So I've got a couple of examples for us to look here in this presentation. Both of them related to using the factor theorem to determine when something is a factor and by extension when something is a root, because the roots determine the factors and vice versa. So this is where it's really kind of getting real for us, right? Because ultimately our goal is to find the roots or factors of polynomials. So now we're going to see how we can use this factor theorem to do that. So I've got this question here. Is x equals 1 a root of this polynomial? Well, the factor theorem doesn't talk about roots, it talks about factors. So the key step to making it work with a question like this is to realize that the question, is x equals 1 a root, is equivalent to asking, is x minus 1 a factor? Because if I set that x equals 1 equal to 0, it becomes x minus 1 equals 0. So that's where the x minus 1 comes from. All right, and answering this question is as simple as calculating p of 1. Right, p of 1 is equal to 1 to the 4th plus 2 times 1 cubed minus 2 times 1 minus 1. And if you get out your calculator or just do it real quick in your head, that does equal 0. And according to the factor theorem, if p of 1 equals 0, then x minus 1 is a factor. And again, kind of working backwards, that means x equals 1 is a root. Let's get a slightly bigger question here. Right, now I want to know, is x squared plus 3x plus 2 a factor? Well, factor theorem doesn't help us with this. Factor theorem only gives us information about linear factors, right, not quadratic factors. So what I'm going to handle this is the same way. I mean, if I asked you, is 117 divisible by 6? Well, I mean, you could do 117 divided by 6 and see what happens. Or you could say, well, look, 6 is 3 times 2. And for it to be divisible by 6, it has to be divisible by 3 and divisible by 2. Both of those kind of subfactors. Since 117 is not divisible by 2, the answer to that's going to be no. I'm going to do the exact same thing here. I'm going to look at that x squared plus 3x plus 2, and I'm going to factor it. And so I get x plus 1 times x plus 2. Now I'm going to say, okay, well, is x plus 1 a factor? And if the answer to that is no, then I'm done. If the answer is yes, then I'm going to say, well, is x plus 2 a factor? And if the answer to that is also yes, then yeah, the original quadratic polynomial is. Right, so to test x plus 1, remember the factor theorem says divide by x minus c, not x plus c. So to test x plus 1, I got to think of that as x minus 1 and evaluate the polynomial at negative 1. And if I do that, I see pretty quickly, there's a calculation right here, p of negative 1 is equal to negative 9, not 0. And so because p of negative 1 is not equal to 0, negative 1 is not a root, which means x plus 1 is not a factor, which means x squared plus 3x plus 2 is not a factor. And there's the answer to my question. So for now, you've got an idea of how to use the factor theorem to determine when something is a factor of a polynomial and when it isn't. And by extension, what the polynomial's roots are and what they aren't. So the big open question at this point still is, what factors should we test? Right? If I'm just given this polynomial and I'm asked to factor it, well, I mean, we got x plus 1, x plus 2, x plus 10, x plus 1,000. You can throw negatives in there. X plus a half, get fractions in there. That's a linear factor. How do we narrow this down? Well, first, the upper link here, if you're interested in the context, that'll take you to the lecture where I derive the remainder in factor theorems. But the second lecture the second link will take you to a lecture on something called the rational root theorem. And the rational root theorem is the solution to that problem. It's a tool that we can use to get a list of all of the possible rational roots, and by extension factors that have rational coefficients for a given polynomial. And it's going to do it in a way that most of the time will narrow it down to a relatively small list of potential factors. Small enough that it's practical to take each one, run them through the factor theorem, and test them to see which ones are factors and which ones aren't.